Some machines look wrong before they even move. One balanced on two wheels taller than a house. Another stretched across the Arctic like a metal centipede. And one is so massive that NASA measures its speed in miles per hour using decimals. They were not designed as jokes. Each was a serious answer to a problem ordinary machines could not solve. The first was Russia's Tsar Tank. Most early armored vehicles tried to crawl over mud in trenches using tracks. The Tsar Tank took a more dramatic approach, make the wheels enormous enough to roll over the battlefield itself. Its two front wheels rose roughly 9 meters high. Between them hung an armored body carrying engines, weapons, and crew. From the front, it looked less like a tank and more like a mechanical siege tower. On firm ground, the giant wheels appeared promising. But the design hit a fatal imbalance. Most of the weight sat behind the front axle, above a much smaller rear wheel. During testing, that rear wheel sank into soft soil. The huge front wheel spun, but they could not pull the machine free. The vehicle built to defeat trenches had been defeated by an ordinary patch of ground. The lesson was not that giant wheels never work. It was that one spectacular solution can create a smaller, less obvious failure somewhere else. Decades later, American engineers faced a different landscape, the frozen north. Oil exploration and military construction required heavy cargo to cross snow, tundra, and terrain with almost no roads. Their answer was the Overland Train, a chain of powered vehicles connected into one enormous articulated machine. Each wheel could help drive the convoy. Steering was distributed through the train, allowing dozens of sections to bend around obstacles. The longest version stretched farther than a football field and carried their own workshops, living quarters, and power systems. Unlike the Tsar Tank, the Overland Train worked. It moved heavy loads through places where normal trucks struggled. But engineering success does not guarantee survival. As heavy-lift helicopters became more capable, they could move urgent cargo without roads, bridges, or a 100-meter machine crawling across the landscape. The Overland Train was not defeated by a mechanical flaw. It was defeated by a better transportation system. Then there is a machine that remains useful precisely because nothing else can replace it. NASA's crawler transporter carries rockets from the assembly building to the launch pad. Calling it a vehicle feels inadequate. It is closer to a moving foundation. The crawler rides on 4 enormous track assemblies. A leveling system keeps the launch platform nearly upright while the road rises toward the pad. Its diesel-electric machinery delivers immense torque, but very little speed. With a rocket on top, it moves at roughly walking pace. That slowness is the feature. The cargo is tall, heavy, delicate, and worth billions. Acceleration matters less than stability. The crawler also reveals why strange machines often look strange. A normal truck is designed around roads, traffic, speed, and cost. The crawler is designed around one route, one payload class, and one unacceptable outcome, allowing the rocket to tilt or shake beyond its limits. Remove ordinary constraints, and ordinary shapes disappear. The Tsar Tank enlarged one component until another became the weakness. The Overland Train solved its original problem but lost to a new technology. NASA's crawler survives because its extreme specialization still matches an extreme task. The weirdest machines are rarely random. They are physical records of the problem their designers were trying to escape. And that is what Impossible Works will explore: real machines, hidden engineering, and the moment a brilliant solution either worked, failed, or became obsolete.